How a MP40 works, invented by Heinrich Vollmer in 1938. Berlin, December 1938. Heinrich Vollmer stands motionless before a metal workbench at the MP40 factory. On the grey surface, steel components await assembly. The body of the device is not solid. It is formed from stamped sheets, folded at precise angles and welded at the edges. The metal stock lies beside it, hollow tubes that slide into the main body. Vollmer touches the edge of one of the plates. The thickness is uniform. No lathe marks, no milling grooves, only the clean geometry left by the stamping press. To the right side lies the massive bolt, the only part still machined with traditional precision. Vollmer lifts the steel mass, feeling its weight, 450 grams of calibrated inertia. He fits it into the body of the device and pulls it back manually. The helical spring compresses under tension. When released, the bolt advances with controlled speed, coming to a rest against the empty chamber. The metallic sound echoes through the workshop. Two engineers watch in silence. One holds a clipboard with technical diagrams. The other notes the cycle time. Vollmer knows what is at stake. The MP38, the previous version, works perfectly, but it requires 60 hours of machining per unit, mechanical lathes operated by specialists, manual adjustments, tolerance control. If a major conflict arises, and everyone knows it will, Germany will need 50,000 submachine guns in the first 6 months. Perhaps 100,000. The math is simple. 60 hours per unit makes the goal impossible. The solution is not in accelerating lathes, it is in eliminating them. But there is a technical contradiction that no one has yet fully resolved. Stamping offers speed, machining offers precision. The bolt needs both. It must slide into the body with minimal clearance, but without jamming. It must withstand repeated firing pressures without deformation. It must maintain exact timing between advance and retreat. Vollmer looks at the machined piece in his hands and then at the stamped body on the table. The question is not whether it is possible to combine the two processes. The question is where to draw the line between what can be simplified and what cannot. Outside the workshop, Europe breathes the heavy air of 1938. Diplomatic agreements are signed and broken. Civilian industries begin to receive discrete military orders. Household appliance factories receive designs for hardware components. The transition is happening quietly. Inside MP40, Vollmer tightens a screw on the trigger assembly. The piece fits without resistance. He notes something in his notebook. The clock on the wall reads 5:01 p.m. The winter light has already faded. Industrial lamps illuminate the cold metal. The device does not yet have an official name, but it already carries the logic that will define it, to function without requiring artisans. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far. And stay with us for the next chapter. Heinrich Vollmer was born in 1885 in Biberach an der Riß, southern Germany. His background was technical, not academic. He learned mechanics in industrial workshops before entering hardware engineering. During the First World War, he worked on the development of light automatic systems, facing the recurring problem of the time: excessive weight. German automatic equipment worked, but required supports, operating teams, and complex logistics. Vollmer observed that the limitation was not ballistic, it was structural. Heavy metals, redundant components, a design that prioritized robustness over mobility. Following the 1918 armistice, the Treaty of Versailles prohibited Germany from developing advanced military hardware. Factories were closed, engineers were relocated to civilian industries. Vollmer worked quietly on sporting designs and industrial mechanical systems, maintaining contact with technical circles that continued researching ballistics and automation in controlled environments. During the 1920s, he studied American manufacturing processes, especially the mass production of automobiles. He observed how Henry Ford had transformed artisanal complexity into replicable simplicity. The lesson was not about cars, it was about method. In 1932, Vollmer joined Irma Werke, a metallurgy company that was starting to receive discrete government contracts. The political context was changing. Treaty restrictions were bypassed through partnerships with foreign companies and experimental production. Vollmer was tasked with developing a modern submachine gun that could replace pistols in close-quarters engagement. The caliber was quickly defined, 9mm parabellum, already standardized ammunition. The rate of fire as well, between 450 and 550 rounds per minute. But the real challenge was something else: how to produce thousands of units without depending on artisanal machining. Vollmer revisited concepts he had studied in the previous decade. Straight blowback, a principle used in automatic pistols, could be applied to submachine guns if the bolt mass was correctly calibrated. Sheet metal stamping, a common industrial technique in household goods, could replace machining in non-critical components. The combination was theoretically viable, but no one had executed it on a military scale. The MP38 was the first prototype. It worked, but it still carried too many machined parts. Vollmer knew he needed to go further. The external pressure was not just military, it was temporal. In 1938, the annexation of Austria and the Sudeten crisis indicated that European conflict was a matter of months, not years. German factories received orders to expand production capacity, but mechanical lathes could not be multiplied quickly. Specialized operators were scarce. The only scalable solution was to transfer complexity to existing industrial processes: stamping presses, welding, modular assembly. Vollmer had 6 months to transform the MP38 into something producible by ordinary workers in converted factories. He did not work alone. Berthold Geipel, Irma's technical director, provided access to testing facilities. Heinrich von Schleinitz coordinated the interface with steel suppliers, but the critical decision belonged to Vollmer. Which parts could be simplified without compromising function? He started with the body, then the stock, then the trigger assembly. The bolt remained untouched. It was still the mechanical heart of the system, but everything around it was redesigned to accept tolerable imperfections. Precision was distributed strategically. The operating principle of the MP40 is straightforward: blowback operation. There is no gas piston, there is no rotary locking system. When the trigger is pressed, a part called the sear releases the bolt, which was held back by a compressed spring. The bolt, a solid mass of steel weighing approximately 450 grams, is driven forward by the helical spring. During the advance, the bolt face pushes a cartridge from the ready position in the magazine into the barrel chamber. The firing pin, fixed rigidly to the rear of the bolt, strikes the cartridge casing at the exact moment it aligns with the chamber. The discharge occurs. The projectile leaves the barrel at approximately 400 meters per second. The residual gas pressure, about 1500 bar, pushes the casing backward. Since the casing is held to the bolt by the extractor claw, the bolt is also pushed back. Here is the essential physics. The bolt mass is calculated so that it begins to move only after the projectile has already left the barrel. If the bolt were too light, it would open early, allowing gases to escape dangerously. If it were too heavy, the cycle would be slow and the system would jam. Vollmer and his team calculated the exact mass through repeated ballistic tests. While the bolt recoils, it performs 4 simultaneous functions. First, it extracts the empty casing from the chamber via the claw. Second, it ejects the casing out of the device as it passes a fixed protrusion called the ejector. Third, it recompresses the helical spring, storing energy for the next cycle. Fourth, upon reaching the maximum rear position, the bolt is briefly caught, but if the trigger is still pressed, the bolt is immediately released and the cycle restarts. This mechanical loop happens about 9 times per second. There is no electronics. There is no computing, just mass, spring, and timing. But the real innovation is not in the firing cycle. That principle was already known. It lies in the physical construction of the body. Traditionally, a submachine gun's receiver was machined from a solid block of steel. The process required removing material by cutting, a slow, expensive operation that generated waste. Vollmer replaced this with stamped steel plates. An industrial press molds the sheet into a tubular shape. Another press adds the openings for ejection and loading. The edges are welded. The result is a hollow, resistant body produced in minutes instead of hours. The stock follows the same logic. Bent metal tubes that slide into the body when not in use. Institutional resistance was immediate. Artillery officers argued that stamped plates did not offer the same structural rigidity as machined blocks. Conservative engineers pointed out that welds could fail under repeated pressure. Quality inspectors demanded durability tests that exceeded normal standards. Vollmer did not argue. He tested. The MP40 was subjected to continuous firing cycles in controlled environments. 10,000 rounds were fired without cleaning. The device was exposed to mud, sand, water, and below zero temperatures. The stamped body held up. The welds did not fail. Simplicity proved to be more robust than complexity. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. Spring 1939. The experimental production line at Werke operates at an accelerated pace. 12 workstations transform flat sheets into device bodies every 8 minutes. Vollmer observes the complete process for the first time outside the prototype environment. The first station cuts the raw sheet to approximate dimensions. The second feeds it into the stamping press, where tons of pressure mold the tubular profile. The third welds the longitudinal seam. The fourth punches the side openings for casing ejection and the charging slot. The fifth installs the internal rail where the bolt will slide. The problem appears at the sixth station. 3 out of every 10 bodies show a minimal misalignment between the internal rail and the central axis of the tube. The difference is 0.4 millimeters, invisible to the naked eye, but enough to create irregular friction in the bolt's movement. The station operator tries to manually adjust each piece. Vollmer halts the line. He does not want manual adjustments. Manual adjustments mean dependence on individual skill. They mean variation between shifts. They mean the line is not truly industrial. The solution comes from an engineer named Otto Brenner, a specialist in stamping tools. He proposes modifying the second station's die, adding internal guides that force the sheet to align automatically before pressing. The modification requires 3 weeks of toolroom work. Vollmer approves. The line stops. Meanwhile, he focuses on another critical component, the ammunition magazine. The original magazine for the MP38 was manufactured from stamped brass, a relatively expensive material with limited supply. Vollmer tests alternatives. Stamped steel works but adds weight. Aluminum is light but harder to weld reliably. He chooses steel but redesigns the internal geometry of the magazine to reduce wall thickness without compromising structural strength. The new version weighs 180 grams instead of 220. It seems trivial, but multiplied by 100,000 units, it represents 4,000 kilograms of metal saved. Metal that can be redirected to other industrial needs. In April, the line restarts with the corrected dies. The misalignment disappears. The rejection rate drops from 30% to less than 2%. Vollmer requests the production of 50 complete units for field testing. 20 are sent to military evaluation facilities. 10 go to extreme test environments, climate chambers, immersion tanks, vibration simulators. The last 20 remain at the factory for disassembly and post-use analysis. The results return in June. No structural failures. 2 units showed bolt jamming after 8,000 rounds. Analysis revealed powder residue build-up on the internal rail. a problem solvable with a slightly modified geometry to facilitate self-cleaning. 3 ammunition magazines showed slight denting on the upper edges. Localized reinforcement was added in the next stamping revision. The rest of the equipment functioned within acceptable parameters. Vollmer notes every detail. He does not seek perfection. He seeks replicable consistency. The difference is fundamental. Perfection requires total control, something impossible in accelerated production. Consistency only requires that the process be predictable and that failures be identifiable. The MP40 is being refined not to be the best submachine gun theoretically possible, but to be the best submachine gun producible at scale by ordinary workers under time pressure. Summer 1939. The first official order arrives, 10,000 units by the end of the year. Vollmer knows that MP40 alone cannot meet the deadline. The solution is to distribute production. Civilian factories in Berlin, Hamburg and Munich receive technical diagrams and component specifications. They will not manufacture the complete device, only specific parts. A metal tube company will produce stocks. An automotive metallurgy plant will stamp bodies. A spring factory will provide the return assemblies. MP40 will assemble and test the final units. But an unexpected discovery arises during distribution. Each civilian factory uses slightly different stamping presses, different pressure capacities, different cycle speeds, different sheet feeding systems. Vollmer realizes that specifications need to be more flexible than initially planned. He rewrites the technical drawings to include variable tolerances. Critical dimensions remain rigid: internal body diameter, bolt rail position, but secondary dimensions can vary within defined margins. This decision to accept controlled variation is the true revelation. Traditionally, military engineers demanded absolute uniformity. Every screw had to be identical. Every component had to be interchangeable without adjustment. Vollmer inverts the logic. Components do not need to be identical if the final system works. A body stamped by a factory in Hamburg might have a wall thickness 0.3 millimeters different from a body produced in Munich. As long as both withstand firing pressures and accommodate the bolt correctly, the difference is irrelevant. This philosophy allows for something revolutionary: instant scalability. When the conflict begins in September 1939, the production capacity for the MP40 multiplies rapidly because new factories can be integrated without the need for specialized equipment. A company that makes aluminum pots can start stamping MP40 bodies in 2 weeks, provided its presses reach the minimum required pressure. It doesn't need to buy lathes. It doesn't need to train lathe operators. It just adapts its dies and follows the specified tolerances. Vollmer's decision also has an unexpected consequence for maintenance. Because parts have controlled variation, field operators cannot simply swap a component from one unit to another without verification. But the MP40 was designed not to require part swaps in the field. If the bolt breaks, a rare event, the entire unit is sent to a repair depot. If the spring weakens, also rare, the unit is withdrawn from service. Field maintenance is reduced to cleaning and lubrication, operations that do not depend on component interchangeability. In November 1939, monthly production hits 3,000 units. By March 1940, it reaches 8,000. In June 1941, it exceeds 12,000. The scalability Vollmer designed is working, but the real test is not numerical. It is functional. Do the units produced at accelerated speeds work as well as the meticulously built prototypes of 1938? Field reports indicate they do. The mechanical failure rate remains below 2%. Average durability exceeds 20,000 rounds before needing overhaul. The stamping logic did not compromise performance. It transformed it into something replicable. Heinrich Vollmer did not live to see the full impact of his decision. He continued working at MP40 during the early years of the conflict, refining processes and developing experimental variants. But the MP40 had already become autonomous. It was no longer one man's project, but a distributed industrial system. Between 1940 and 1945, approximately 1.1 million units were produced. Most were manufactured by workers who had never touched such equipment before, in factories that had never produced military hardware. The technical legacy of the MP40 is not in its ballistic performance. Other submachine guns of the era were more precise, lighter, or quieter. The legacy is in the method. Vollmer demonstrated that automatic hardware could be treated as mass industrial products without losing functionality. The lesson was absorbed globally. The British Sten, developed in 1941, took simplification even further: a fully stamped body, less than 5 hours of total labor per unit. The Soviet PPS-43 adopted similar principles. The American M3 grease gun followed the same philosophy: stamping, welding, minimal machining. More significantly, Vollmer's logic transcended hardware. Accepting controlled variation, distributing production among non-specialized factories, and designing for manufacture instead of designing for perfection, these concepts became foundations of modern industrial engineering. It was no coincidence that the same era saw the rise of modular production in aviation, vehicles, and electronic equipment. The global crisis forced engineers to choose between artisanal excellence and replicable scale. Vollmer chose scale, and it worked. There is a subtle historical irony. The MP40 was conceived to solve a manufacturing limitation, a lack of specialized lathe operators. But in solving that problem, Vollmer created something broader, a template for how to design under the pressure of limited resources. The device works not because it is ingenious, but because it accepts its own limitations. The stamped body will never be as rigid as a machined block, but it doesn't need to be. The heavy bolt will never be as light as a gas piston system, but it doesn't need to be. The MP40 works because each component does only what is necessary, nothing more. Today, the stamped body is standard in light hardware. Many modern designs utilize some form of stamping in primary components. The transition, Vollmer codified, became irreversible. But the deepest lesson is not technical. It is philosophical. Effective engineering is not about eliminating compromises, but about choosing the right compromises. Vollmer did not try to make the perfect submachine gun. He tried to make the submachine gun that could exist in sufficient quantity when needed. And by accepting that limitation honestly, he created something that survived long after its era. When Vollmer adjusted that pin in 1938, he wasn't just finishing a prototype. He was codifying a paradigm shift. Complex systems do not need to be artisanal masterpieces to function under pressure. They need to be replicable, reliable, and compatible with the industrial logic of their time. The MP40 works because it accepts this condition without resistance, and that is why, decades after its production ceased, its influence remains visible in every assembly line that prioritizes consistency over perfection. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.